Hello and welcome. In this video, we're going to take a look at another kind of function, one that we call a vector field. Now, by the name there, you can imagine that this is going to be a function that gives us a vector. So it's like a vector function, except that it's a vector function of multiple variables. So it's going to be tough to graph this one, I think. But let's take a look at the definition. A vector field is a function f with a vector over the top here. Well, maybe we'll use capital F so that you know this is a vector field and not just a vector function. And it's a function that maps from u to v, where u is a subset of Rm and v is a subset of Rn, with m and n both being dimensions greater than or equal to 2. Okay, so a couple examples here so you know that these are not just your normal vector functions. If we wanted to have a vector field of 2 dimensions, x and y, it could be a vector of 2 dimensions, let's say. So for any x and y, maybe we end up with a 2-dimensional vector xy comma negative x squared. We could also then take a look at maybe a 3-dimensional vector field. And here I'm using points in space x, y, z, and those correspond to vectors in 3-dimensional space as well. Now remember, with this definition, it is free to actually have a function of 3 variables give you a vector with 2 variables potentially. But in many scenarios, we'll probably be thinking about 2-dimensional points with 2-dimensional vectors and 3-dimensional points with 3-dimensional vectors. Now, how do we graph these things? You can imagine that might not be an easy thing to try to represent. All right, well, here I've got a nice little example. Let's say we've got the function f of xy equals x minus y comma x. Well, we could do a little table of values here. Let's pick a point, maybe not the origin, but let's pick a point, let's say 1 comma 1. And you plug that into our function and we find out that, well, the x component is 0 and the y component is equal to 1. All right, so at the point 1, 1, let's graph that as being the initial point of our vector f of 1, 1, which is 0, 1, so it should be pointing straight up with 1 unit. Okay, well, let's just pick another point here and see what ends up kind of becoming a problem very quickly. Let's just jump to a different quadrant. Let's pick a point negative 2 comma 3. When we plug that in, we see that the x component of our vector is negative 5, and the y component is negative 2. If we try to graph that vector, it's going to be, quite a long vector with the initial point negative 2 comma 3. Okay, so you can see the problem here. That's going to make it very hard to graph all of these vectors all over the map and be able to kind of understand which way they're pointing when they're all overlapping each other. So let's take a look and see how software like Maple will actually try to plot this for us. It might make a little bit more sense. So here I've got with plots to include a couple of additional plotting tools, and I'll show you both a 2-dimensional and 3-dimensional example. So here's a function 3 comma 1 minus y, and its vector field in red. Now you can kind of interpret this. Well, maybe don't click on it. You can see that, of course, all of the x components are 3. So they're all pointing to the right. None of these vectors are 3 units long, though. What Maple is doing for us is it's scaling them all down so they will fit into a small grid. You can see the grid is kind of defined by how many arrows it's going to try to plot for us. So they will never be overlapping, but they are never actually the correct magnitude. You'll see, though, that the y components, 1 minus y, that's not always the same. And that will, as y is increasing or decreasing, affect the vertical orientation of each vector. And if y is equal to 1, then these vectors should be horizontal. And you can kind of see that right here at that y equals 1. You'll notice that not all these vectors are the same length. At least they have a kind of a nice scaling. So longer vectors have more magnitude than shorter vectors. Okay, now what about a 3-dimensional example? Here, g of x, y, z is 1, 1, 1. Okay, so they're all constants, but let's just see how Maple graphs that. Of course, we have a nice cube here. It's a 6 by 6 by 6 cube centered at the origin. You can see that all of these vector arrows, they're sort of harpoon shaped. They're all pointing in the same direction right now. It gets a little bit more interesting when we start putting some variables in here. Now we'll be a little bit careful. Let's say 1 over x, y, and z. See what happens. Ooh, it got crazy. Okay. Totally bizarre. That's how we represent this vector field. And you can kind of maybe make some sense here. As x gets larger, this is going to get smaller. So looking around the x-axis here, they are pointing in opposite directions on the x-axis, but then pretty soon you'll find that when x equals 3, they're not pointing left or right along the x-axis anymore. But y and z, as they grow, they get larger. You can see for y equals 0, the vectors lie in the xz plane. But as y starts to increase, so does the y component. And same thing with z here as well. Well, as z increases, you can see that the z component increases. So you can take a look at the sort of 3 different sides here and try to make sense of that. Okay, well, you might be trying to think of some practical applications of vector fields. And really, any kind of application where you want to associate a direction and strength or magnitude to any point in space. One example would be a magnetic field. And every point in three-dimensional space around this magnet here would have a magnetic field with a given strength and direction. Or maybe we want to think about velocity. We might want to think about the velocity of wind traveling over this cross-section of a wing, let's say. And that will give us the idea that air might be traveling faster over the top of the wing and slower over the bottom. And we can see the direction in which wind is traveling. Okay, or another kind of field, a gravitational field. And if we're given some body of mass with mass capital M here, and some other mass, maybe with a little mass, little m, if we place that at any point in space around the mass, we can think about the magnitude of this force and the direction. And it should be attracted towards the other mass, and that gives us the direction. And by an inverse square law, we can understand the magnitude of that force as well. In fact, the gravitational field is a great example to start with. And you might remember from other classes in physics, you might remember a quick inverse square formula that gives the relationship between the magnitude of the force of gravity between two masses and the radius or distance between them. So by Newton's law of gravitational force here, you can see F being our gravitational force without a vector on the top, this is simply just the magnitude, is equal to a gravitational constant G times the two masses, capital M, usually represented as the larger mass, the little m is maybe the smaller mass, and r squared, where r is the distance. Now, if you want to start making that into a vector, we need to make sure that the vectors are pointing in the right direction with the right magnitude. Well, we've got the magnitude here. What we want is if we place the mass, capital M, at the origin, and we think about this smaller mass maybe being somewhere out here in this picture up in the top right, we want this to be traveling towards the origin. So if we take its position, we can represent that as r being the vector, x, y, z, or you could think of this as being a point, x, y, z with round brackets. Well, we want this to be pointing towards the origin. So that's going to be in the reverse direction of the position vector. To make this a vector field then, we're going to have this being in the negative direction of our position vector. But unfortunately, the position vector doesn't have a magnitude of 1. So we want to make sure that that's a unit vector. We divide that by the magnitude of that position vector. Of course, whenever we're looking at the magnitude of that position, r with a vector symbol over the top, we will just let that be r. And so this gives us a vector field that is equal to negative gmm over r cubed times the position vector r with a vector symbol over the top. Now, this is a little different notation. We can actually rewrite this as a vector field in terms of position r. Now, if you want to think about this as being more conventional in terms of x, y, and z components, then of course, that's not too hard to do. We've got r being the vector x, y, z, and that means we can calculate the magnitude of r. If we wanted to write the gravitational force formula in terms of x, y, and z then we can write that as negative gm little m over x squared plus y squared plus z squared, all to the 3 halves, because we have that square root being cubed, multiplied by x, y, z. And that's just a scalar, so that could actually be distributed onto each component if we wanted to write the whole thing inside the vector. Now, I've kind of prepared an example of that here in Maple, so you can take a look. And let me maybe zoom this in a bit here. Oh, you can see I've removed that G, M, M from this, and I've just kind of let M and little m and G all be ones, just so that it's easy to plot. But I've got the minus sign, so that's going to help with the correct direction. And you can see I've got that x squared plus y squared plus z squared to the 3 halves in here. And you can see that each one of these vectors is pointing towards the center, which is, you have to imagine there being a mass right there, with the strongest force being when the two masses are very close, and weak force being towards the edges of this cube. So yeah, if I wanted to maybe zoom in here a little bit more, it might make things easier. You can see exactly what we're expecting. Strong force towards the center, near the center, and weak force towards the center, farther away from the center. Now, another great example of a vector field, you may have seen this before. We get vector fields when we look at the gradient of a multivariable function. Remember that for a function of, let's say, 3 variables, the gradient is simply the vector of the 3 first-order partial derivatives. And of course, this can be expanded to as many dimensions as we like. A function of n variables, the gradient is simply just a vector of each of the n first-order partial derivatives. You might remember that one interpretation of this gradient is it's a set of vectors at every point in space that will be orthogonal to the level surfaces of the function. That definition may always be a little bit tricky to try to interpret, so I've got a little animation here that might try to help with that. I'll just zoom in here a little bit. I've got a function f of x, y, z, which is x squared plus y squared plus z. Now I'm using that as a function of 3 variables, and I'll plot the gradient of that. Now the next thing here is a little animation. I'm plotting several of the level surfaces of the form f of x, y, z equals k. Luckily, I know this. I can just solve this for z to make this a function x, y, which will make it easy to plot. And so I'm plotting that from k equals 0 to 2, several level surfaces corresponding to different values of k. And we'll see what this looks like. Now you might have been able to guess the shape of this. I have x squared plus y squared plus z equals k, and I have a paraboloid simply being shifted up and down depending on the value of k. You can see each of these vectors is perpendicular to this level surface where k is equal to 0. And if I animate this, and you can see different values of k, no matter where that level surface is, the vectors are still perpendicular. So that's the gradient field of this function and the level surfaces, and you can see that they are always perpendicular. All right, so if we happen to have a vector field that is just actually the gradient of some function, then we call that vector field a conservative vector field. And that's going to have some great applications that come up a little later in vector calculus, and we'll understand why it's called that. Now, there's also a term for the function. So let's say if we have capital F, the vector field, equal to the gradient of little f, the function, then we say that that function is the potential function of that vector field. Again, there are some applications, and you may have heard that term potential in terms of gravitational potential. So this may just all come together as we start taking a look a little bit more into depth on vector calculus. Thanks for watching. I'll see you in the next video.